Hi, this is Jack Polson, and this is the second of two videos on a JOLT on collective communication. The first video covered broadcast in a lot of detail and gave two different algorithms. Now this video is going to be much shorter and will describe the reduce operation, and we'll then go over a few different very easy applications of it to do some useful computation. Okay, so now we're going to describe the absolutely simplest way you could possibly think of using this reduce operation. So in particular, suppose you have P processes and each one of them has some vector, say on the ith process it has some vector x sub I, and you would like to give the sum of all of these different vectors to one particular process. So if we look at the formula, you'll see that this is just a summation of a large number of vectors if you have a large number of processors that you want to give to one process. Okay, so this is called reduce. So it turns out that you can really just run a broadcast algorithm in reverse, except for each time that you receive data from another process, you perform a summation of that data that you received with the data you already had. So what's important is that the communication costs are therefore the exact same as for performing a broadcast. Okay, so naturally we're not limited to actually just using summation here. We could perform some other sort of binary operation, like we could take an entry-wise maximum, or we could take the product of the two different floating point entries. You can do many different things here, but it's easiest to think of summation for now. Okay, so the routine that you call looks a lot like the routine for broadcast. But rather than having just one buffer that you pass in, you have both a send buffer and a receive buffer. So the send buffer needs to be contain data on every single process, and then the receive buffer will only be filled on the root process that you specify upon completion of the algorithm. So here you have to specify an additional argument versus broadcast, which is the operation that you would like to perform. So in most cases, this will be MPI underscore sum in all capital letters, which would sum these different vectors over this team of processes. And then you specify the process that you would like to receive the result via its rank, and then you give the communicator that you would like to perform this operation over. So again, this is the team of processes that you would like to use for this collective communication. So again, it reduces each processor's n items of data over a specified communicator and gives the result to a particular process. So there's some related routines. MPI all reduce is probably the easiest relative. Rather than giving the result to just one process, it gives the result to every single process. Yet another is MPI Reduce scatter, which instead of giving every process a full copy of the result, it gives every process a piece of the result. So this would be the same as if you ran MPI Reduce and then you ran MPI scatter immediately afterwards. So suppose you wanted to perform an inner product between some vector y and a vector x in parallel. One obvious way to do that would be to give each process some contiguous subset of the entries of x and the equivalent subset of entries from y. Say x sub I and y sub I on process I. Then a natural way to do this would be to think of breaking up this inner product into the sums of the inner products that you could compute locally on each process. So in particular, the first step of the algorithm would be for process I to perform the inner product of its portion of y with its portion of x, and to store that in some scalar, say alpha sub I. So after this, you could then perform a reduce on this single scalar that each process would have a different value for, and then give the result to a single process. So given the analysis that we had for broadcast, what we can see is that if we ran a binomial reduce, where we can think of the vector length of being 1, then the cost of the communication would be alpha plus beta times log 2 of p, where again alpha is the latency cost for sending a single message, and then beta is the bandwidth cost for sending a single entry. So the floating point work that would be required for these local inner products in this case would look like 2 times n over p, since each process would have roughly n over p entries of x and y if x and y were each of length n originally and we had p processors. So this is essentially optimal. The only difference is, or the only cost for performing the communication is this alpha plus beta log 2 of p term, which is actually quite low. Okay, so setting y equals x would naturally yield an obvious way of computing the 2 norm of a vector x, and then setting y equal to all 1s would yield a parallel way to compute a 1 norm of x. So if we want to be a little bit more sophisticated, now we could think of how we would compute, say, the infinity norm of x in parallel, which is just the maximum of the absolute value of the entries of x. So I apologize for missing the absolute value here. Okay, so what we would do is we'd give each process a subset of x, say, again, x sub I, and then locally each process would compute the infinity norm of its portion of x. And then once you have this local infinity norm, you can then run an MPI reduce where you specify the operation this time to be the maximum as opposed to doing summation. So when two processes exchange their scalar, which is their current maximum value, each process then stores the maximum between those two different values. So this is just like the distributed one norm, but again, we use the maximum binary function as opposed to summation. Okay, so that concludes this video on a jolt on collective communication routines. Thanks.